It's another exciting day here in Algebra 2. Today we are going to look at logs and exponential functions, specifically their graphs. Now, we do have some experience previously this year with exponential functions, but a quick recap. Remember, our parent function is a to the x, where a is your base, and a cannot equal 1. When a is greater than 1, we have exponential growth, increasing graph, and when a is less than 1, we have decay or a decreasing graph. And the reason that a cannot be 1 is because 1 to any power will always be 1. So that graph would just look like the horizontal line y equals 0, which does not have the characteristics of an exponential function. So this is not an exponential function, therefore a cannot be 1. Now let's jump straight into some graphing. We're going to first graph our parent function and then some different transformations. So like always, I am going to start by making a little table here with some x values that I know I can get on my graph. So if x is negative 1, 2 to the x, 2 to the negative 1 is 1/2. If x is 0, 2 to the 0 is 1. If x is 1, 2 to the 1 is 2. If x is 2, 2 squared is 4. And if x is 3, 2 to the third is 8. So this is 5 points that I know will fit on my graph, and I am going to use those as I graph each of my transformed functions as well. So there is my graph. So as far as the transformations, this is the parent function, so there are none. For domain, I have all real numbers. For my range, y is all values greater than 0. We are increasing, walking uphill. I have a y-intercept at 0, 1. And I have a horizontal asymptote at the x-axis, which is the line y equals 0. And so that is our asymptote here. And this is going to be my frame of reference as I move on to the rest of these. So on 2, I have 2 to the x minus 3. The minus 3 is with the x in my exponent, so that tells me it's a horizontal shift. And because it is minus, that means I am shifting right 3. So what I can do instead of setting up a new table with new inputs and outputs and doing the calculations myself, what I can reference is this original table and look at my transformation. If I'm shifting right 3, that means my x values are going to change, and they are each going to increase by 3. So 2, 3, 4, 5, 6, and then those y values will stay the same. So here are 5 new points on our transformed graph. And I skipped one, pause. Got a little ahead of myself. Nope, I see what I did wrong. Apologies. This is where I got a little ahead of myself. Okay. So there is our transformed graph. Looking at our new characteristics, my domain is still all real numbers. My range is still all y values greater than 0. I still have an increasing graph. Our y-intercept, however, has changed. It's not on my table. I can kind of eyeball it on the graph, but to actually find it, what I need to do is substitute 0 for x in my function. So that would be 2 to the 0 minus 3, which is 2 to the negative third. With negative exponents, that means it's on the wrong side of your fraction. So I have 1 over 2 thirds, or sorry, 2 to the third. So that's 1 over 8. So my y-intercept is at 0, 1/8. And then my horizontal asymptote did not change. We are still at the x-axis, y equals 0. Okay, moving on to 3, I have 2 to the x minus 3. That is now no longer part of the exponent, so that means that we are shifting down 3. So I'm going to refer to my original table, not the one from part 2, but on my original table, shifting down 3 means that my y values are going to change, and they are each going to decrease by 3. So I'm going to set up a new table and subtract 3 from each y value. And then my x values will remain the same. Okay. So looking at this new graph, my domain is still all real numbers. My range has now shifted though because I have shifted down. I now have all y values greater than -3. We still have an increasing graph. My y-intercept is now at 0, -3, or sorry, 0, -2. And then I have a horizontal asymptote now that is related to my new range. That horizontal asymptote also shifted down 3, and it is at the line y equals -3. Okay, moving on to the next row, I have -2 to the x. That negative on the outside tells me that this is a reflection over the x-axis. So again, referring to my original table from graph 1, if I'm reflecting over the x-axis, that means the sign of my y values is going to switch. So if they were positive, they become negative, and vice versa. So each of these y's will become negative. And then all of my x's will stay the same. So here are new points that I can graph. And so my graph has flipped upside down. We still have a domain of all real numbers. My range is now all y values less than 0. Our graph is decreasing. I would be walking downhill across that. Our y-intercept is now at 0, -1. But my horizontal asymptote did not change. It's still at the x-axis y equals 0. Okay, on 5 I have 2 to the -x. This time the negative is in the exponent, so this is also going to be a reflection, but this one is going to be over the y-axis. So I'm going to again refer to that original table from number 1, and this time instead of changing the signs on the y's, I'm going to change the signs on the x's. So all the negatives will become positive and vice versa, and my y coordinates will remain the same. So this graph got reflected, kind of mirror imaged around itself. So this domain is still all real numbers. My range is still all y values greater than 0. We now have a decreasing graph. We would be walking downhill. My y-intercept stayed the same, 0, 1, and so did my horizontal asymptote. It's still at the x-axis, y equals 0. Okay, last one. On this one we have 2 parts. We have that reflection over the y-axis again, and we're going up 2. So reflect over y-axis and up 2. So what I could do is go back to that original table from number 1 and do the reflection and the shift up, or I can now reference the graph from 5 because this one already has the reflection and just shift this one up 2. So what that would mean is I'm going to take the table from graph 5 and add 2 to each of my y values. And then those x values will remain the same. And here is our new graph. This one still has a domain of all real numbers. My range is now y values greater than 2. We still have a decreasing graph. Our y-intercept is now at 0, 3. And my horizontal asymptote has also shifted to y equals 2. That horizontal line. So, to summarize what we have here, our parent function had a domain of all real numbers, a range of all positive values, a y-intercept at 0, 1, an increasing graph, and a horizontal asymptote at y equals 0. And then when we had to the negative x power a decreasing graph of reflection over the y-axis, all that changed was that our graph switched from increasing to decreasing. So these are your default characteristics, and depending on different transformations, these could change. Now the same is true for your natural exponential function as well. If you have e to the x, it has all of those same characteristics, and the same goes for if you do that reflection over the y-axis. So let's get into the log function now. Remember, logs are inverses of exponential. So if I refer back to that 2 to the x that we just looked at, and I'm just going to look at 4 of those points that we just were graphing over and over again. If I wanted to find the log, remember, inverses are just switching x and y. So to graph the log for log base 2, all I would need to do are switch the x and y pairs in my table, and I can now graph these 4 points, and I can graph my log function. Now, again, thinking back to what we just discussed, in an exponential function, your domain is all real numbers, your range is all positive values, you have a y-intercept at 0, 1, it's an increasing graph, and you have a horizontal asymptote at y equals 0. Well, if I look at the graph I just graphed now, the log, my domain is no longer all real numbers, it's now all positive x's. My range is now all real numbers. Now I have an x-intercept at 1, 0, still an increasing graph, and instead of a horizontal asymptote, I have a vertical asymptote at x equals 0. So your inverses truly switch all the x and y's in your function. All of the respective x and y characteristics did switch. All right. The same is true for our e to the x, and now this one's not very pretty, not perfect numbers, so we're just going to have to estimate a little bit here. Remember, e is that number that's approximately 2.718, so we can still just kind of eyeball some of these numbers. So e to the 0 is still obviously going to be 1. We know e to the 1, 2.718, e squared, 2.718 times itself. I trust that you could do that by hand if you really had to. And then e to the negative 1, 1 divided by 2.718 would be 0.368. So that's my exponential with base e. So the natural log, that is a log with a base of e. Again, you're just going to switch your x's and your y's. They are inverses of each other. So these are now points that I can, again, just eyeball and graph. And here is my natural log graph. And regardless of how perfect or imperfect that becomes, we can still identify, you know, our characteristics for the exponential and how that changes when we graph the log, our inverse. Our domain is now x is greater than 0. Our range is all real numbers. We have an x-intercept at 1, 0. Still an increasing graph, and now you have a vertical asymptote at x equals 0. Okay, with all that in mind, we are now going to graph some logs with different transformations, and I am going to get cut off with time for this video, so I am going to start a part 2 for the rest of these.